This video is about sigma notation, also called summation notation. Sigma is the actual Greek letter that we use, and we call it summation notation because it tells us to add up the terms in a sequence. So let's start with our first example. The number below the sigma sign is the first term number. So the starting term number. The one above is the ending term number. Let me point out that that is not the number of terms in the sequence always. Sometimes, in this case, since we start with 1 and end with 4, there are 4 terms in the sequence. But if you look below, and if we start with 0 and end with 3, there are still 4 terms in the sequence. So that number above does not tell me how many terms I have, just the ending term number. Then the 2n squared plus 1 is the rule for finding the terms in the sequence. And I don't know why I wrote root, that's supposed to be rule. So if you start with n equals 1 and apply the rule, you'd have 2 times 1 squared plus 1. Then when n equals 2, you'd have 2 times 2 squared plus 1. When n equals 3, you have 2 times 3 squared plus 1. And when n equals 4, you have 2 times 4 squared plus 1. And according to the sigma notation, that's where I stop. Now, the sigma itself means add up. It's sum. So we're going to add up all the numbers that we get doing this process. The first number we have is 3. The second number turns out to be 9. The third number is 19. And the fourth number is 33, just by doing 2 times 3 squared plus 1, 2 times 4 squared plus 1. Then I add those up and I get 64. So the sum, as n goes from 1 to 4, of 2n squared plus 1 is 64. So it's a single number here that I get as an answer. Now the next one starts with 0 and goes to 3. So we just start counting with, and this uses the variable k instead of n, so it doesn't really matter what you use. J, k, I, and n are usually the most commonly used variables in a sequence in summation notation. So I'm going to write my 4 values for my term numbers. So I've got term numbers 0 through 3. And then I'm going to substitute 0 through 3 into here for k. So I have negative 1 to the 0, and then 2 times 0, plus negative 1 to the first times 2 times 1, plus negative 1 squared times 2 times 2, plus negative 1 to the third times 2 times 3. Now I want you to notice what happens with this negative 1 to the k. And I'm going to go ahead and, even though I know this whole thing's going to equal 0, I just want to write this out. This becomes negative 1 to the 0 is positive 1. So I have positive 1 times 0, plus negative 1 to the first is negative 1, so I have negative 1 times 2, plus negative 1 squared is positive 1, so I have positive 1 times 4, plus negative 1 cubed is negative 1, and then times 6. So notice what happens with this. I end up with 0 plus negative 2 plus positive 4 plus negative 6. The next one would end up being positive 8, and so forth. What this term does is causes the signs, or it causes the terms to have alternating signs. Okay, so the terms alternate signs, and that is kind of a handy little way to make the terms alternate signs. If I add this up, I end up with negative 4. Now the next one, the new feature I want to introduce here, is the infinity sign up here. This just means that we have a sequence that starts with 2 being my term number and goes on forever. So we can't technically add this one up, although we will find that there are some infinite sequences that we can add up. So we'll start with j equals 2, j equals 3, and so forth, maybe one more, and then I'll just put dot, 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 plus dot, dot, dot. So when j is 2, I'll have 2 over 2 plus 1, so that's 2 over 3. When j is 3, I'll have 3 over 3 plus 1, so that's 3 over 4. The next one will end up being 4 over 5, plus, and then so forth, and just put dot, dot, dot. So substituting numbers into sigma notation is pretty straightforward. You just plug the numbers in, compute the terms, add them up. But when we go backwards, it's a little more tricky. When I give you a sequence and say write summation notation for it, that's a little more challenging. So let me give you a few tips. First of all, check to see if the sequence is either geometric or arithmetic. If it's either geometric or arithmetic, then you're just going to use the explicit rule that you already know how to write the rule for the summation notation. So for example, in number 1, you have an arithmetic sequence where each time we are adding -15 plus -15, or I'll just say we're subtracting 15, that's easier. -15, -15, -15, and so forth. So you've learned 2 ways to write an explicit rule for an arithmetic sequence. One of them is to say, start with the first term and add d, -5, -15, n minus 1 times. The second way is to say, I know that this is a linear function. This will end up being a linear rule where -15 is the slope, so I have -15 times n, -15 times n plus a constant. So if n is 1, I'm supposed to get 100. So I would need to add 115. So -15 times 1 is -15 plus 115 gives me 100. Another way to look at this is if this is term number 1, 2, 3, 4, 5, and 6, if I go back and look at term number 0 and continue this pattern backwards, term number 0 would be 115 because that would be 15 less than 100. And so when n is 0, then this number would be 115. Now I would suggest, even if you write the rule this way initially, that you go ahead and multiply this out, simplify it, and get it down to this form. Now when I put this in summation notation, and just a helpful hint, draw 2 parallel lines, make the little V shape, and then add those little 2 pieces there. That's the easiest way to make the summation notation. I'm going to start with n equals 1. I have 6 terms here, so I'm going to end with 6 on the top, and then I'm just going to put the rule. You don't write the a sub n equals part, you just write the rule, 15n plus 115. So you are just writing shorthand, compact form for this sequence. The next one is a geometric sequence. I'm just going to tell you that. You know how to figure that out. Remember, you can say 500 times r equals 400. R equals 400 divided by 500, which is 4/5 or 0.8. And then you can double check to make sure that 400 times 4/5 gives you 320, and 320 times 4/5 gives you 256. It does. I'm just going to tell you that. So to write a rule for an geometric sequence, you take the first term, 500, and then you're going to be multiplying by 4/5 n minus 1 times, so you raise it to the n minus 1 power to get to term number n. So to write our sequence rule, to write this in summation notation, we're going to start with n equals 1. Now notice here I have 4 terms, but I also have this on the end. So this tells me I am going to be going to infinity up here. So this is going to be an infinite sequence here. And then I'll put my sequence rule in here, 4/5 to the n minus 1. So here is summation notation for number 2. Now in number 3 and number 4, we get to sequences that have patterns that are not arithmetic or geometric. You do have to be able to find an explicit rule. You cannot write summation notation with a recursive rule. So we have to be able to figure out some sort of an explicit rule. In order to figure out an explicit rule, we have to look for some sort of connection between the term number and the terms in the sequence. So if I number my terms, n equals 1, 2, 3, 4, and 5, my tip for you is number 1, if it's a fraction, look for a pattern in the numerator and look for a pattern in the denominator and just write those patterns separately. Okay, think about a separate pattern for the numerator and a separate pattern for the denominator. Number 2, if the signs alternate, leave that part till the end. Ignore that at the beginning. So I see two things going on. My numerators are always 1. So part of my rule is that my numerator is going to be 1, because it's always 1. My denominator is 3, 4, 5, 6, 7. My denominator is always 2 bigger than my term number. So if my term number is n, then I would call my denominator n plus 2. So the 6th term would be 1 over 6 plus 2, 1 over 8. And the 7th term would be 1 over 7 plus 2, 1 over 9. Now I've dealt with everything except the alternating signs. I want my first term, my third term, and my 5th term to be positive. So notice that my odd terms are positive and my even numbered terms are negative. So the even terms are negative. So I have to use, I have to raise -1 to the correct power so that the odd terms will all turn out to be +1 and the even terms will all turn out to be -1. Well, if I raise it to the nth power, that means all the odd number, when n is odd, I'm going to get -1. Well, I don't want to get -1 for the odd terms. I want to get +1 for the odd terms. So I have to make this n plus 1, or n minus 1 would also work. So for example, when I put 1 in for n, I get -1 squared, which is positive. When I put 2 in for n, I get -1 to the third, which is a negative number, making my second term negative. So this is my term rule. So if I go over here to write this, I would have n equals 1 to 5, 1 over n plus 2. Actually, that doesn't need parentheses around it. I'm not sure why I put the parentheses. Let's try this again. N equals 1 to 5, 1 over n plus 2 times -1 to the n plus 1. I could also just write -1 to the n plus 1 in the numerator as well. That would be the same thing. Now, just to let you know, there are other ways to write this. For example, I could write, I'm just going to show you two other ways quickly. I could start with n equals 0 instead of n equals 1. I could go from 0 to 4. If I went from 0 to 4, my denominator now is going to have to be n plus 3, 1 over n plus 3. And then I do -1 to the n. So that's the only advantage to this one at all. I don't know if there's really any advantage at all. But now my, since I started with term number 0, so my term numbers are numbered 0, 1, 2, 3, and 4, that means that I can just use n for my exponent here because -1 to the 0 is +1, -1 to the 1 is -1, and so forth. Another way that I could write this would be looking at the denominators. Instead of making my term numbers 1 through 5, I could make them 3 through 7. And I could start with n equals 3 and end with n equals 7. Then this would just be 1 over n. And then I would still have to write this -1 to the n plus 1 because I would want my odd numbered terms to be a positive term. So I'd have to make the exponent even here by adding 1. So these are all three different ways to write example 3. There's no one way that is more correct than the others. So whatever you notice about the pattern, you can write it that way. Now example 4 is a little bit trickier. Example 4 doesn't have an obvious pattern to begin with. You might want to pause it and see if you could figure out the pattern for a second. If you can't, then I will be glad to tell you. I noticed I would like to look in the numerator for a pattern and the denominator for a pattern. So first of all, this isn't even written in fraction form, so it would probably be best to think of this as 1 over 1 first of all, as a fraction. However, I noticed my pattern 3, 1, 5, 3, 7. It might be nice if this was 3, 4, 5, 6, 7. Okay, so that would make the pattern in the denominator a little better. So let's rewrite this. So this is 1 over 3. This is 1 over 1, or 1, so I could write this as 4 over 4. Then this would be 9 over 5. The next one is written as 8 over 3, minus 8 over 3. So I could write it as 16 over 6. multiplying both numerator and denominator by 2, and then this would be plus 25 over 7. And this is definitely what you want to do, because not only do we end up with a really nice pattern in the denominator, 3, 4, 5, 6, 7, just like what we had before, but we end up with all perfect squares in the numerator. So I could say then, if my term numbers are n equals 1, 2, 3, 4, and 5, my numerator is just going to be the term number squared, 1, 4, 9, 16, 25. The denominator is just going to be n plus 2. And then because my odd numbered terms are positive and my even numbered terms are negative, just like they were in the first way that I wrote example 3, then I would have to have negative 1 to the n plus 1. I'm not sure why I didn't put the sigma notation down first so I could just write it all at once, but this would be n equals 1 to 5 n squared over n plus 2 times negative 1 to the n plus 1.